welcome to the 8th seminar in a series of research seminars hosted by Nomadic Labs. Today's speakers are Everett Hildenbrandt and Stephen Skeirik, both from a company called Runtime Verification, dedicated to developing the Semantics framework and using it to improve the security of smart contracts platforms such as Tezos blockchain. Everett has worked at Runtime Verification since 2018. His background is in physics and computer science, and his goal is to make tooling based on formal methods accessible and cheap for everyone. Stephen joined Runtime Verification in 2020 after obtaining his PhD in formal modeling and verification at University of Illinois and Urbana-Champaign. His goals include grounding system design on practical logical foundations, which enable real-world design and system formal verification. If you have questions for Everett and Stephen, please write them in the chat during the presentation, and I will ask them at the end. So let's start with Everett's presentation entitled Bringing K-Powered Blockchain Security to Tezos.
Thanks, Raphael. So our talk is titled Bringing K-Powered Blockchain Security to Tezos. I'm Everett Hildenbrandt, and Stephen Skeirik is with me. We'll be sharing this presentation. We'll be starting off with just an overview of blockchain security in general, and then talking about what that means in terms of vulnerabilities and how to mitigate vulnerabilities, and then focus a little more on what RV has done in this space, specifically focused on tool-based approaches to vulnerability mitigation, some prior work for the Ethereum ecosystem, and then Stephen will take over and talk about how we are porting a lot of this work and experience to the Tezos ecosystem via the KMichelson semantics, and then a little bit about KVM and future work after that. So this will be a bit of a high-level talk, but feel free to ask any questions about anything technical you'd like, and we'll get to them at the end. So just an overview, probably not something that has to be discussed in super depth, but just an overview of what blockchain security looks like today. The first thing to know is it's obviously profitable to try to attack blockchains and smart contracts. There's a lot of money locked up, and if you can find a vulnerability, you might be able to exploit it to get money out of it. But there's a lot of ways to exploit vulnerabilities in blockchain, and some of them, like social engineering, illegal pressure, or phishing, or stuff like that, we're not really focused on. That's more of operational security stuff. But as far as the actual smart contracts themselves or the system design themselves, that's more what RV's wheelhouse is. So that'll be things like designer vulnerabilities or code vulnerabilities, and what are the mitigation strategies we can use to eliminate these as sources of funds lost, basically. So an overview of what a design vulnerability is, because these are the two major classes, are design and code vulnerabilities. A design vulnerability is a flaw in the business logic, is what we call it, of a blockchain or smart contract. So an example for a blockchain itself would be if you had like a proof of stake system or a proof of work system where someone found a way that they only need to control a small percentage of the network to affect double spends or to revert the history or something like that. So this would be an example of where the blockchain itself has a design problem that leads to people being able to exploit it without having the 51% or whatever it is you assume is the necessary amount to exploit that. An example for a smart contract design issue would be if you introduce some mechanism into your smart contracts that was meant to be positive. So for example, maybe you want some mechanism to promote liquidity on distributed exchanges or something like that. So you introduce that into your smart contract system, and someone finds out, oh, this mechanism, while it's implemented correctly, actually can be over leveraged in this corner case, which is illiquid markets, to drain your liquidity pool tokens. So this is kind of a contrived or just random example. I don't know if it's actually realistic or for anything. I'm just coming up with ideas here, but the idea here is that you have something where you have a smart contract system, you introduce a feature to it, that feature is implemented correctly, so there's nothing wrong with the code, but the feature itself exposes some problem with your overall design that allows someone to exploit a corner case and make money off of it at the expense of others on the system. So that's kind of what a design vulnerability is. And then to mitigate design vulnerabilities, there's a couple techniques. The first one would be, make a specification of your design, and you want to be as detailed as possible. In the specification, explore every corner case, make sure that everything is specified. And oftentimes people make an initial specification or a white paper, and then you come back and audit that specification. You realize, oh, you didn't actually consider these 5 different cases, and one of these 5 cases is maybe exploitable, something like that. So that's why it's important to be detailed, to have diagrams, flow diagrams between different contracts and stuff. Audits are another good way. So you'd have someone audit the design specification itself. So maybe you write a white paper, an auditor comes in and makes it a bit more rigorous by putting in mathematical models. If you're in some sort of thing where there's some dynamics going on, maybe they write down some differential equations describing the system and do some proofs about those, showing that they're stable in the way that you want. You can also, instead of using an on-paper model, which is what the specification would be, you can make a computer model of it. So an example of a computer model would just be an implementation. You can just make an implementation of it and then run it on a bunch of tests. So another word for tests is simulation. So run a bunch of simulations on it. Or you can use an actual modeling language, which, basically with any of these modeling approaches, you're then going to poke the model a bunch until you're convinced that the model behaves as expected. And verification really just means that you poked the model so much that you proved that there aren't any issues. You've explored every single possibility, either symbolically or exhaustively. So that's kind of the mitigation strategy for design vulnerabilities. Once again, there's kind of the human-based approaches, which is the top 2 bullet points, and then the tool-based approaches, which is the bottom 2 bullet points. A code vulnerability is where your design is good, everything looks like it should work, the differential equations describing your system behave stably in the way that you expect, everything's good. But the code that you implement has a bug in it. So this is more what people think about when they think of exploits. So an example of the blockchain would be that maybe there's one client that people are running as their full node, that's the most popular one, and there's some part of the code that lets people sneak in a bunch of transactions without them being confirmed or something, and then they're able to do the double spends because the network says, oh, they're confirmed when they actually haven't been confirmed or something. And it's a problem with the code where there's some, synchronization issues or something. So maybe the client is able to trick someone into thinking they've paid them $40 million. The code issue is worked out the next week or something, but that doesn't mean that the person they tricked into spending the $40 million gets their money, gets their whatever they're paying for back, right? An example with a smart contract would be, just not using safe math where you should. So this is kind of this is the example that most people are most familiar with is, somewhere in the smart contract system, you have a bug in your code, which lets people burn, all of the ETH that's locked up in the parity multisig or something like that, right? So examples like that. Okay, so these are kind of more common ones. And once again, there's a lot of mitigation strategy. Simplest one, testing, right? And testing is something everyone should do. Most people are familiar with. So, highly recommend, definitely do testing. And there's a couple different types of tests. Unit testing is what most people are familiar with. Regression testing, definitely something that's underused, and it's just, if you found and fixed a bug, make sure you write a test that would have caught the bug, right? And then that means that you won't accidentally reintroduce the bug later. Audits also applicable for code review. That'll look for, general programming errors, logical errors. So logical errors here would be something like so there's, some mathematical expression that when implemented over the real numbers, so in your design, you implement it over the real numbers and it looks good. But when you implement it on Ethereum, the specific order you do the additions and subtractions and multiplications and divisions, for example, can lead to maybe unbounded error due to the conversion from reals to integers. And we actually found an issue like this in the very first version of Uniswap, where someone was able to, you'd be able to manipulate the way a division happened in the code to get arbitrary exchange rates on Uniswap, which is obviously not a desirable property. So there's an example where Uniswap's mathematical formula in the design was fine, but their implementation in EVM, specifically there was a division that happened in the implementation. They were doing a multiplication and a division, and they did the division first and then the multiplication, which meant they were dividing some smaller number and then multiplying it to make it a bigger number. If you flip that around, you do the multiplication first, then the division, then you're dividing some larger number and there's a smaller error. But anyway, the way it was happening allowed you to get arbitrary exchange rates. And so we just refactored the code a little bit, and then we were able to prove some bounds on how much error there would be in the exchange rate. So things like that. Another one would be analysis, so like static analysis tools, which look for some specific problems and report them to the user, or other tools which provide a summary. So I said broadly static and dynamic, and then full formal verification once again. So this is not design verification or design modeling, but here it's showing that the code doesn't have any side conditions you haven't considered, basically. So it's just making sure that you've exhaustively checked that every piece of code works as intended. So yeah, those are the two basic categories. You got the design vulnerabilities and the code vulnerabilities. We have mitigation strategies for them both. And RV is kind of focused on the auditing and tooling side of things. So the auditing side is kind of, our services offering, but the tooling side, we're trying to make tools that people can reuse between all the blockchains, and they can use themselves, ideally, before even approaching us for an audit, to make sure their own code is high quality before that way the audit goes a little quicker. So yeah, so kind of what I've already been saying, if there's tooling available, then mitigating these vulnerabilities is a lot easier. Not even introducing them in the first place is a lot easier, because you can continuously use the tooling as you're developing. But kind of the problem we're seeing is that there's lots of new blockchains coming into existence. Some of them are small tweaks on the existing ones, so you can kind of reuse tooling, and some of them are very different, right? So Tezos and Ethereum don't share much at all in terms of the underlying VM that's running, right? There's not a whole lot of similarity. You can't reuse KEVM to try to do verification of Michelson contracts, for example. So somehow there's this lack of tooling for new blockchains coming into existence, which means it's hard to attract devs, and it's also hard for devs to make sure that the contracts they're deploying reach the same level of security and assurance that is expected, for example, in the Ethereum ecosystem. So that's kind of the story. And here it is again. There's too many tools, and this is not focused on runtime verification isn't just focused on blockchain. That's why these languages listed here, like C, Java, JavaScript, these are all languages we have semantics for and we have offerings for. But the traditional approach to developing tooling for a given language is that, okay, so you pick one language like C, and then you pick one tool like the compiler, and you say, I'm going to implement a compiler for C, right? And then you pick another language like Solidity, and then you pick another tool like a model checker, and you say, I'm going to make a model checker for Solidity, right? And this is kind of a lot of wasted effort, because there's not a whole, like abstractly, a model checker is a model checker is a model checker, right? Like you don't want to have to re-implement a model checker for every new language that you are trying to model check programs over, right? So this is a little bit unfortunate of a situation, but this is how people have been developing tooling for programming languages, since the beginning, basically. So the K approach, and there's other tools that take this approach as well, but the K approach is, somehow we should have something in the middle that allows you to build the tool itself separately, the interpreter, the compiler, the model checker, Symbolic. You can build that once, and build the language itself separately, which we call semantics, build that once, and kind of get the entire cross product of tools and languages, quote unquote, for free. We say for free, but it's, obviously it's not free, because you have to develop the language, you have to develop the tool, but with less effort than the original approach, which has this kind of, much larger combinatorial explosion going on. So this, ideally it'd be linear in the number of languages and linear in the number of tools, right? And then an update to the model checker benefits every language that is using that model checker, right? Or an update to the verifier benefits every language that's using that verifier. So this is the approach K tries to implement. And, I say try because for the most part it's successful, but there's parts that we find, okay, there's kind of rough edges. There's some stuff we have to do that's specific to Java, or there's some stuff we have to do that's specific to Ethereum, which means that work is not portable to the other languages, but that's okay. At least we're getting 80% of the work to be portable between all the languages. So what is K? Just broad overview. K is what's called an operational semantics framework. So what does that mean? It means you specify your language or your system. It doesn't have to be a programming language. It can be an arbitrary system. You could make a model of a car or something in K, in the K modeling language. And then the K compiler takes that model that you've made and derives all the tools on the right-hand side for you. So you specify your language like Java or your model of a car, whatever like that, and then K compiler will then spit out on the right-hand side, here's an interpreter for you, here's a model checker for you, here's a symbolic execution engine for you, and here's a deductive verifier for you. So that's kind of the K approach. We have two main backends which are used to power all of the tools that are generated. And then all the tools are basically written as wrappers around these backends. So we have the LVM backend. So when you write a K specification, the compiler will spit out a bunch of LVM code, which will implement a fast interpreter for you. So now you'll have an interpreter for your programming language. And then we have the Haskell backend, which is for symbolic execution. And that symbolic execution, we have further wrappers around that, which are completely language independent. They don't care about what language you're coming from. That turn that symbolic execution engine into a model checker, and into a verification engine. So all of the tools that are built by RV are powered by K. That's kind of our little slogan, powered by K. And all of our smart contract verification that we do at RV over the years is also done with K. So once again, just to give you a little glimpse of the architecture of K, there's LVM backend, the Haskell backend. LVM backend is used for things like the interpreter and a parser, which isn't shown here, and stuff like that. And then the Haskell backend is used for like the model checker, symbolic execution, and deductive verifier. It's slower than the LVM backend, but it's able to do symbolic reasoning. So trade-offs, Okay, a little bit of prior work, and I'm assuming these slides will be made available afterwards, so you can follow the links yourself. I might open a couple of them. But KEVM is kind of our most prolific prior work. And it's just a K semantics, a K specification of the Ethereum virtual machine. We run it on the same conformance test suite as all the other clients. So we know it's compatible with like Geth and Parity and these other large clients that run the huge Ethereum conformance test suite. But it also is able to do symbolic execution, which enables verification of EVM bytecode. So that's different than the other clients. There's a lot of tools out there that can do some type of symbolic execution or verification of EVM bytecode. Most of them have some sort of ad hoc encoding, like maybe you have like a Python symbolic execution engine that is able to take a piece of EVM bytecode, execute it symbolically, and assert some properties about it, but you don't know if that Python implementation actually agrees with what Geth or Parity is going to do because it's too slow to run on the conformance test suite. So that's kind of one of the big differences between this semantics-based approach and a more ad hoc approach where you just make a tool that's specific to doing, verification of EVM in Python. So a couple of prior things that we've done. Here's an example standalone K proof. It's very verbose. I just want to show how verbose it is. But here's your bytecode that you're trying to verify, and we're trying to verify specifically the transfer function. And we're transferring to some account, and we're transferring from the caller ID, right? And this is how much we're trying to transfer. And this is the success case. So we end in EVMC success, which is the status code for success. And the output is just Boolean true right here, which is what this one is. And then if we look at the storage, we see that, the caller IDs balance. I know that I'm going through this quickly, but you have to trust me that it's saying what I say it's saying. The caller IDs balance goes from, some prior balance to the balance minus the value. And the two IDs balance, which is the function we're calling is, ABI encoding of the transfer function where we're transferring to this account, this amount of money. the two IDs balance goes from the original balance to the balance plus the value, right? Then there's a bunch of side conditions here that basically say, okay, and nothing happens that would cause this to fail. So for example, the value that's being transferred is less than or equal to the original balance of the caller ID. That's good. And then also that the balance being transferred to plus the value doesn't overflow, right? Because that would cause problems with your token. So if you didn't have this side condition and your verification went through, then all you verified is that you have a token which allows overflow, which, you know, maybe you want that, but you probably don't, because people's balances can get pretty wonky. So it's an example case spec. Most people are not dealing directly with these case specs, but basically, you know, you can tell K, okay, now verify that this spec actually holds. And what it will check is this code that's supplied right here always has the property that when you transfer from caller ID right here to 2ID, this amount of money, and you know that there won't be an overflow, and you know that the value is transferable, then the transfer will go through correctly, basically. And then there's another spec here. You know, we have the transfer success 1 spec. There's a transfer success 2 spec. And then we also have to have transfer failure specs, for example, which say, you know, that instead of it going through successfully, it will revert or hit the invalid instruction or something like that. So it's the same code here, same call we're making, but the side conditions are going to be different. So in this example, the value is greater than the balance from, right? So here we're saying, okay, if they're trying to transfer more value than they have in their account initially, then every single time when they're trying to transfer more value than they have in their account initially, we expect that it hits the invalid instruction and does not continue execution. And if you ask K to prove this, what you're showing is that indeed every single time that you try to execute this code and you have the condition that the value is too high, it will hit the invalid instruction. So it's kind of a detailed look at that proof. We don't have to, you can look at the proof yourself more on your own. But once again, most people are not writing these proofs directly by hand. Anyway, so we have some other tooling which kind of wraps up this very verbose way of writing it into some easier ways of writing it. Not going to go super into depth there. You can follow the links and kind of get a feel for what that is. Just want to also show off some other KVM-based projects that have happened in the past. So for example, the Uniswap V1 audit I mentioned, we developed this lightweight symbolic analysis way of doing audits, which is a lot lighter weight than doing full proofs, but kind of allows you to reach a large amount of the same guarantee, but it's cheaper. It's the main thing. We've also done just full verification, so where we write down that specification I showed you, but for an entire contract. So an example of that was the ETH2 deposit contract, which allowed people to take their ETH from the ETH1 chain and move it to the ETH2 chain so they could begin staking and stuff like that. We actually found bugs in the Viper compiler doing that, which led to the re-implementation of that deposit contract in Solidity because people weren't confident that the Viper compiler was doing the right thing, basically. And there's an example here with the DAI, multi-collateral DAI system, the stablecoin, where there's 1,011 proofs written in K. And this isn't a good example to look at to see what high-level language you could write down the specifications in and get the K automatically generated from, so you don't have to write it yourself. I'm going to quickly go through a couple more things. So this slide was kind of focused on verification. That's been a lot of our wheelhouse. Recently, we've been trying to focus more on testing to allow people to write the code, write the test themselves, or improve their quality of their code without having to learn full formal verification. So we have the Firefly tool, which is a coverage and testing augmentation tool, basically. You can take a look at it here. The basic thing it gives you is coverage, but it also will do a little bit of random testing for you. And some property testing is in the plans. You can look at the About page there, see what's planned. We have the ERC20 verifier, which is a property tester you can submit code to, and it will come back and say, yes, this is a ERC20, or no, it's not, right? So I'll show you what that looks like real quick. The report here, this is an example that is not in ERC20. So it comes back and it says all these specifications we have for ERC20s failed. So you can submit bytecode here. Our servers will kick off and run the bytecode. And then it will give you some sort of summary saying, okay, this is the test I ran, which is, I make a new symbolic ERC20, and I set all its storage to completely arbitrary things, and I set the from address, the to, and the value to arbitrary things, but I make sure the value is greater than the balance from, and I expect that we're able to make the transfer. And somehow, because we're getting the failure here, that the transfer is not able to be made. But this tool allows you to write tests, symbolic tests directly in Solidity. It's not as powerful as writing the K directly itself, but it's a little more comfortable for Solidity devs. This is an example of a tool that we will eventually be porting to the Michelson language as well, to allow people to do property tests over Michelson and do lightweight verification over Michelson. So yeah, anyway, you can look through the slide here to see some of the prior work we've done with KEVM. And, just remember, it's all powered by K. And then, this back to the main thesis here is, we're porting to other blockchains, Michelson being one of, Tezos being one of them with the Michelson language. And we get a really nice economy of developer time doing this because there's a lot of work that we don't have to redo at all. And then there's some work we do have to redo, but at least now we have a template for how to do that. So it ends up being a lot quicker. Okay, yeah, so some examples of, I'm not as much of a Michelson expert as Stephen, so I apologize. I'll be flubbing my way through the rest of this presentation. That's okay, though. Yeah, some examples of other languages we have. We have KELA, which is a register-based VM that we helped design for Cardano, for example. And we have KWASM. KWASM itself is the WebAssembly semantics, so it actually can just be used as a standalone WebAssembly interpreter. Which means you could theoretically hook it up to a browser and use it directly as the WebAssembly interpreter for the browser. I'm not sure it would be advisable. I don't know if it's not really optimized for that. But we can specifically, hook that up to other embeddings of WASM for other blockchains like Polkadot and Elrond, and then basically get a lot of the same tooling for those blockchains, right? So we get the Firefly tooling, we get the verification tooling, all that stuff for other blockchains as well. So yeah, and then KMichelson, we have the the GitHub pages documentation in the Michelson language. You can visit the page here and kind of get an overview of what the semantics looks like and how to get the installation working, stuff like that. So download it, try it out, try to run the test suites, see if you can follow this user guide and try out some of the examples we have there. And then you can also just go to the Michelson semantics directly and see, okay, what the syntax definition of Michelson looks like in K. And so here it's all, K. I'm not going to try to make this into a K lesson, but at least for me, K is easy to read. I know it's kind of foreign to a lot of people, but here we're defining the syntax of the Michelson language, which means, okay, we define the syntax of identifiers in the language as regular expressions for what are allowed as those identifiers. Define the syntax of types in the Michelson language. So here's the base types that you would expect to be there, stuff like that. Data literals. So you can go through this and take a look. These are the syntax of contracts, right? You have your code declaration, stored declaration, parameter declaration, or it can be in this order. So it's just every possible order. It's probably possible to also do this without enumerating every possible order, but it actually ends up being more efficient for the parser to just enumerate them all. So why not just do that? And then the individual instructions that you can have in the Michelson language listed here. So this file in particular just basically shows this is what the syntax of a Michelson contract is. And then somehow we have this internal syntax as well. So what's going to happen is the K semantics will take a Michelson contract written in this syntax, and then it will convert it into the internal syntax, which allows us to more easily define the rest of the semantics over. So that's the syntax of Michelson. Probably common is not as interesting, but you can go to Michelson itself, which will define the configuration. So the configuration in K is a way of saying this is all the state needed to model this programming language or this system or whatever it is. And this is the initial values we expect in that configuration. So this is all, notice here that everything is, all the code blocks have inline in them, the markdown documentation. K actually just reads the markdown file directly, extracts the code block, so it allows for literate programming, which makes it really easy to write this type of documentation. That's nice. So you can read through this and get a better idea of what the Michelson runtime looks like. This is probably the main meat of it right here. The K cell is what's going to actually hold what's being executed right now in the Michelson language. So whatever instruction it is that's up next to be executed will be here. And then the stack, this is going to be the Michelson stack. So, okay. But there's a bunch more stuff you have to look at, and then you actually look at, okay, when you set the storage using the storage command to T, then go over to the storage type and set it from not set to T, right? So you update it at the same time. So, but like I said, not a K tutorial, but feel free to take a look at that and get a better idea. Oh, Stephen, are you back?
It seems I think I'm back now. So sorry guys, I was having some internet issues. I hope to not have any more.
All right, hand off the presentation to you.
Awesome. Do you mind going back to the slides? Okay. Hey guys, so I'm Stephen Skeirik, a formal verification engineer at Runtime Verification. So I've been working on the Michelson semantics for a little bit now. So I'm going to talk about that next. So if you bump the slide for me, Everett. So essentially, the Michelson semantics in KMichelson has been this ongoing collaboration between the Tezos Foundation and Runtime Verification. So we have done 3 separate engagements. The first one just to define the Michelson semantics in K. The second one was actually we created a simple unit test harness and also a conformance test harness where that we can cross-validate our K implementation against the reference client. And then for this most recent engagement, we actually extended the semantic tooling we had with these symbolic execution and deductive verification capabilities that Everett mentioned earlier. So that's just an overview of kind of what we have done up to this point. Everett, could you go to the next slide for me? So just some quick facts about how hard it is. How hard is it to set up all this stuff? How much benefit can you get from using a K-like system? So basically, we have around, I think, 5,000 lines of code, give or take, and about 450 tests. And so then that's not a lot of code actually, but what do you get, with that code? So if you go to the next slide, Everett, for me. So we have, our interpreter. We have the documentation website. We have the unit test runner. We have the conformance test harness that tests our interpreter against the reference interpreter. We have a symbolic test runner, and we have a program verifier. So 6 tools for 5,000 lines of code that I and some other collaborators had to write, and that's all because of this, essentially, quadratic, I think, power or leverage that you get from using a framework like the K framework. So anyway, yeah, just another quick facts page. So Everett actually is already talking about this, so maybe this won't be as interesting for us, but I was going to show you an example rule from the semantics. So you have the add rule. This is just add from Michelson that you know and love. As you know, there are annotations in Michelson. Currently, our semantics ignores annotations because they're actually quite tricky in some corner cases, and they also cannot make a they only make valid programs invalid. They can't change if your program doesn't have them and it if you remove them, essentially it only affects type checking in a very limited way. And that's a good way to say it. But anyway, in this rule, we have a type stack. So we have 2 number types and the rest of the stack. And then we, based on those number types, we generate a new number type, which basically says if either of them is int, the result is int. And then we just add the 2 ints together, I1 and I2, using this plus int. That's like the built-in int operator. And Everett already talked about the different cells that we have. So the K cell stores the current continuation, and the stack stores the stack. So that's pretty straightforward. So next slide, please. So here's just an example about how you actually use the tool. So suppose that we want to use the unit test runner. How are we going to do that? So setting up a unit test for any language requires setting up your code and also your input. So in the case of a blockchain language, we have some contract code we need to test. We also have the storage of the contract that we need to specify, and sometimes we need to specify metadata about the transaction, depending on if the contract needs to use that, like the sender or whatever. In this case, it'll be simpler than that, so we'll just see how we can set up a simple test on the next page. So basically here we have this vote.tz contract. It's pretty straightforward. You check if you have enough money to run this contract, and then you basically look up some key in a map, which has an integer value, and you increment it by 1, and then you store that map back in your storage. So pretty straightforward. And now, to run this contract with some input, we'd have to specify in the storage, you have to specify an amount, specify, the key that's going to be our, input parameter. And then we also want a final storage. That's what we expect to see when we finish running the test. So how can we do that? So basically, we keep the code as it is, but we can append some extra fields. These aren't valid Michelson, so this isn't actually a TZ file anymore. We call it a TZT for TZ test. So this file format was developed in collaboration with Nomadic Labs, and basically it allows you to specify your test parameters in line with your source code. So once we have done that, and just basically copied those test setup parameters over to our file in sort of the obvious way, using essentially, the notation is a little bit more heavyweight. You have to have this stack_else, which isn't a part of Michelson. So we had to invent some notation for the stack values, because obviously in Michelson, you can't directly grab a stack. So in any case, move on to the next slide, please. So all you have to do is just use our script runner, KMich, and you give it the interpret command, and then you pass in your TZT test, and then it'll run the test for you. And the test runner will provide 2 pieces of output for you: a process return code, which indicates whether the test passed or failed, and also the final state of the semantics or the interpreter when it stopped execution, which either happens when the whole program is finished executing, or when that you get stuck, which is more likely to happen when you are, testing things symbolically. So typically with a concrete test, you will not get stuck. That's a bug. So in any case, go on to the next slide, please. So we also can run symbolic tests. Now, this is such a silly little test, but I just wanted something really easy. So, again, this isn't just a Michelson interpreter. This is a Michelson semantics. That means we can execute fragments of contracts that aren't actually complete contracts. Here it's just an add instruction. And we can also test our program symbolically. So here, we have actually replaced our input and output stack literals with variables. So we have these three variables, $I1, I2, and I3. And in the input stack, the interpretation of a variable says for all variables, for all values of this variable, execute the contract and see what it does. And the meaning of a variable in the output stack says, basically, does there exist a value of this variable that matches what the actual output stack is? So that's essentially that. Now, this test isn't very interesting, so we can make it more interesting with a post condition that says, the final integer that we get is odd. And so we specify post conditions in our modified sort of TZ2 format with a list of Michelson blocks of type empty stack to bool. And this post condition basically just says that if you divide I3 by 2, the remainder is 1, which is equivalent to saying that I3 is odd. Now, this test will fail for the simple reason that if you give any NAT I1 and I2, and you do the division, the result will not always be even or odd, excuse me. So that's not going to work. So we're going to have to do something to fix it. So we can add some preconditions via a similar mechanism. And here we just add, two precondition blocks, one that says that I1 is odd and one that says that I2 is even. And then you now have that what you expect, which is that the test passes successfully. So just a simple test to just show off, what we can do. Obviously, you can push this a lot farther, and we do. We have examples with loop invariants. We have examples with symbolic lists and sets and maps. So there are more interesting examples, but this one is just easy to show to you guys. So go on the next slide, please. So essentially, the K-vision really, this, like Everett was saying before, is that we plug in our formal language definition, our syntax and our semantics for whatever language it might be, and then we get all of these tools out. This effort has really been going on for over a decade. It started off as a research program, and we have been trying to make it so that this isn't just something that's confined to the realm of academia, but is available to end users anywhere. So here's kind of a tooling tree that shows sort of, in some sense, how we have developed tools and dependencies between them. So the green boxes show what has already been done in the previous three engagements. So we have a compiler, we have a parser, an interpreter, a test runner. We also have a symbolic execution engine, a symbolic test framework, and we also have the theorem prover capabilities, which just derive directly from the symbolic execution engine. So those are all things that you can play with today. And starting actually very soon, in this coming week, we are working on test case coverage. So what this means is that we'll add a new mode. And actually, could you go to the next slide for me? Because I think this will be relevant to this. So we'll add a new mode where that basically the semantics will execute your program and with some set of inputs, and then it will check for each instruction that that instruction has been covered all possible ways that you can execute that instruction. And so, it will generate a nice report for you. We have reporting technology that we've used for other blockchain languages, and we're going to port that to Michelson. So, just the simple green means all covered, yellow means partially covered, red means uncovered. And again, because we're semantics based, that means that every way that an instruction can get executed is tested. It's not just that you passed the line or something. there's actually, in some cases, 5 or 6 ways, that you may be able to execute one instruction, depending on if it overflows, or maybe it succeeds, maybe you make a jump, there's all these different possibilities that, might come up. So yeah, if you go to the next slide for me, please. So kind of coming full circle, effective auditing of smart contracts and really any program requires humans, obviously, to be present to kind of specify what even the overall goal is. What are we trying to achieve? That's the human inspection part, but also tool-based analysis, because oftentimes the state space of these systems is either too large or maybe too tricky to follow manually. And so the idea, again, is that from a single semantics, like for example, KMichelson, we want to have the ability to derive tooling that can do full fault verification, but also kind of lightweight symbolic analysis, and that can give you more insight into the quality of your code and your test suite. And as Everett mentioned, we have similar tooling that's been developed or in development for other chains, and so I think that's a big part of our overall value proposition, is that no matter what blockchain you're using, we'll support it. And we'll also support, future versions of the same tool. So yeah, so I think that's all that we have. So thank you so much. Are there any questions?
We do have some questions. So we have a question about the TZT test format. So the question is if it's possible to have several tests, like input-output pairs for the same contracts.
Right. Currently, no, that wasn't part of the original specification. So I agree, that's a shortcoming of the format. So it's something that we do want to address in this coming engagement, especially since this engagement is about coverage testing. That means you need to have a lot of input-output pairs that you're running all at once to see, if your contract is covered. So no, not now, but we are aware of that, and we do want to improve upon that.
So not yet, but it's coming.
Yeah.
Okay, thank you. I have a question about the very last point you mentioned, which is about the future versions.
Right.
So one strength of Tezos compared to most other blockchains is its ability to evolve through on-chain governance, and this is both very nice and also quite a lot of work to follow this moving target. So do you have any suggestions to what could be proposed to the community regarding Michelson? And so do you have ideas for how the language should evolve in the future to make your work and the work of other people in trying to apply formal methods to Michelson easier?
Oh, that's a very good question. Wow. I'm not sure if I have an answer right off the top of my head for that. Everett, do you have any thoughts about?
Sorry,
about how to answer that question?
Can you repeat?
Well, I'll tell you. Basically, how can the language? So the Michelson language is designed to evolve, and how could the language be evolved so that it can better support, verification by tools like the K framework, like KMichelson? I'm just trying to think about in general, even what features do we want a language to have to make it easy to work with, to verify?
Well, that's hard to say without going and trying to verify a bunch of Michelson programs. But I can just tell you about our past experience a little bit. So we started off doing serious verification with KEVM as the first semantics we were doing that with. And one of the things we found is just that the way, you can write down the specification of the Ethereum virtual machine multiple ways in K and get the same interpreter in the end, but it might not be as there's some ways that are better for formal verification than others. So we found a bunch of ways we could rewrite parts of the K specification of the EVM that made verification easier, basically. And I'm sure we'll find the same thing with the KMichelson semantics. We'll end up rewriting parts of it. So just in the process of trying to verify Michelson programs, I'm sure we'll find certain corner cases or stuff like that that make it hard to do verification. We can suggest changes to the Michelson language itself that allow, the same basic semantics, but maybe a different verification. A simple example of this would be like the gas calculation in EVM has historically been really hard for us to do verification with. Recently, we came up with an abstraction that makes that a lot easier, but maybe there's something to do there where there's there's some little bit of the Michelson language, like gas calculation expressions, stuff like that, that makes it hard to do verification. We suggest a simplification. Another thing that has made EVM hard, for example, is there's a bunch of different schedules for EVM. There's the different hard forks like Istanbul and Petersburg and yada, yada, yada. And if you have that makes the logic for doing a lot of the verification harder, actually, because you have to basically every time there's a change in the hard fork, you have to add more checks to the semantics. Okay, are we on the hard fork that adds this opcode? Are we on the hard fork that changes this gas expression, something like that? But you can make hard forks that simplify some of those things as well, and then you still have the check, like, are we on that hard fork? But then the operations themselves become simpler. So I don't know. It's hard to say without actually going out and verifying a bunch of Tezos programs. So.
Right. No, I hear what you're saying. Those are some good points. Oh, I'm getting some feedback. I think one thing that I noticed when I was working with Michelson programs is that the annotation system sometimes is quite tricky. Again, it doesn't actually do anything to the actual semantics of instructions aside from, make the type checker reject more programs. So you don't need it to do any, you can do all the work you could do without the annotation system, but I found that part to be tricky to get right, and that for doing a full type checker, you had to process the annotations in a very specific way. So we gave up on that. So maybe if there is a way that annotations could be simplified, somehow that could simplify writing other type checkers for Michelson.
Yeah, so everybody hates Michelson annotations. So actually, there is an open discussion on totally ignoring them for the future. And so currently, I haven't heard anybody asking for them to remain there. So it's okay. So this suggestion is probably going to happen unless a new.
Okay. But I do want to say that one thing that is nice about K with respect to language updates is that language updates present the same kind of problem as writing a whole new language, because you now need to update your compiler, you need to update your interpreter, your parser, your theorem prover, whatever tools you have to update them all separately in the standard model, right? Now with K, you update your semantics, one time, and then, you can derive these new versions of the tools from that one specification, again, not entirely for free, but with much less effort than you would if you had to update each one individually, especially because typically they share almost no code and they have different developing teams and styles. And so, again, I think that this is really helpful with dynamic, in the sense of evolving languages like Michelson. So.
Okay, thank you very much. I think we are getting to the end of this session. So thanks again, Everett and Stephen. Thank you to all attendees. And for the next session of this Nomadic Labs Research Seminar, we'll have the pleasure to welcome Steve Purcell and Arthur Bretman, who will present the Checker RoboCoin. So please welcome them for the next question, for the next session.
Thank you. Thanks so much for having us.
Thank you, guys. Yeah.